presentation will begin momentarily. We're excited to share our hard work and show off the projects of our team members for our at-home audience. For more details, please visit multirotor.mst.edu.
Hi everyone, a huge thank you to everyone who showed up here today. This is an incredible turnout, way more than we expected. We're so happy to have you here. This is a project that we put a lot of time and effort into, and we're excited to share it with you all. First off, I'll be handing the mic over to our CEO, Jesse.
Huge thank you to Rose for that amazing introduction. As you guys can tell, this stand's a little bit short for me, so I got my own special microphone. How's everybody doing today? All right, cool. Hope you guys are all super excited to be out here. I know we are. We've been working on this project for such a long time, and we're super excited to finally get to show everyone what we've been working on. So, I know a couple of you guys might be asking yourselves, who is this Multirotor Design Team? Why am I here? What is my objective being here? And to answer that question, we have prepared all this because we want to educate you guys on what our team is, what we do, and what your sons, daughters, anyone on this team is doing as they're talking about the Multirotor Design Team that you probably hear about quite a bit. So I got quite a few people after me that are much smarter than me that are going to be giving you guys a rundown on how drones work, how our drone specifically works, and also the competition that we have built this drone for. The competition is very in-depth, detailed, and we have spent many months designing the perfect drone for this competition. We are super excited to show you guys everything that it should be able to accomplish this year. I'd like to say a quick shout out to all of our sponsors this year. Huge thank you to Powerline Systems for being super willing to donate, to match all donations going towards our competition travel. They are the reason that we're gonna be able to go to this year. And then also I wanna say a massive thank you to Cube Pilot, Northwest Blue, and all of our other sponsors that you guys will see on our sponsor table for donating both monetary and physical donations. If any of y'all would like to help us out with that competition travel, we still do need quite a bit of money to make it to that. So if you guys wanna, after this, the table first out here on your right, that's our donation table, so go talk to the lady running that and she will help you get that all set up. I just wanna say one more quick thank you to everyone on this team. You guys are what made this team succeed these last couple months, and your hard work is what got us to this point. Massive thank you to all of you.
Thank you so much, Jesse. You have been a fantastic CEO this year, and we're so glad that we have you heading our team. Next up, we're going to be hearing from Trey, who is a grad student and consultant. And let me tell you, this guy has been on the team since I've been in like middle school. This dude's old. Come on up here.
Thank you, Rose. That's kind of crazy thought, actually. That's really weird. All right, so this drone that we've built that we're here to show you guys today, what is this? What are we doing? Our team participates in the Student Unmanned Aerial Systems competition, or SUAS, as we like to call it lovingly. You may have heard that around when you were exploring the tables today. SUAS is an autonomous delivery competition. So we have built a drone, sort of like you might have seen on the news for Amazon or like with Walmart's Drone Up. And our goal is to deliver water bottles. This competition is with 72 other universities from around the world. So we're competing with the likes of Purdue, with UCLA, lots of different Missouri S&T rivals, I suppose you could say. And we're very excited to bring what we've got to the scene and show off all the tech that Missouri S&T has and show what we can do. The competition is, it's really cool. We have, our drone has to take off in 30 minutes. We have to fly a 3-mile circuit. We have to detect our drop targets. There's gonna be 5 of them. We have to drop the water bottle within 20 feet of that target from above the 75-foot limit. And then we have to, like I said, repeat that 5 times before we can land. Ooh, lost my arrow keys there. Like I said, this is an autonomous competition, so all this stuff is cool. You may have heard it. Some of you guys may have flown drones before. Because it's autonomous, we have to do this all without a pilot, and that is by far the hardest part of our competition. All right, so the competition is graded based on point scale. So it's weighted 70-30 for performance versus documentation. The performance is how many of those water bottles can we drop accurately, how many of the rules we can follow during the physical time on the day. And then 30% is the technical design, so all the documentation, all the videos, everything that we do leading up to it. If you haven't seen any of the Missouri S&T design teams before, we are a famous school in the community for having design teams with a ton of documentation. So we're definitely looking forward to submitting all of that and seeing what people can think of our designs. All right, and then the competition itself isn't the only thing we have to worry about. There's lots of nitty-gritty considerations we have to make, and we have to think about these things up front during the design process. So things sort of like, are there other drones operating in the area? There's 72 teams competing. There's supposed to be 3 or 4 at a time. We can't hit them, right? Are they looking for us? We don't know. We have to look out for them. We have to avoid those ourselves. We have to make a delivery from way up in the air. How are we going to do that? How are we going to get the water bottle down to the ground? We can't just drop it and bonk somebody on the head. They're not going to be having a good time if we do that, right? Can we carry all the bottles at once? Will our drone be too heavy if we try to do that? If we land and we have to reload, that takes part of our 30-minute time, right? So do we have enough time to do it that way? And then finally, how does our drone see those targets? I mean, you guys have webcams in your computer, right? But does your computer have computer vision? Probably not. So our software team has to figure out how to do that. The 4 guys after me are 4 of our greatest student engineers, and they're going to come up here and they're going to talk to you about the overview of the system and show you some of the problems that they've had to solve. All right.
Thank you, Trey. Hopefully that gives you all a bit better of an idea of some of the challenges we face going into this competition. Next up, we're going to be hearing from Luke, our chief hardware engineer, and he'll be talking a bit more about the physical systems of the drone.
So hardware. We made the hardware of the drone, the mechanical parts. That's kind of, in the name there. That's not any team-related project. That is my homework. All right, so frame design. Well, let's go through some of the things. This mic is on, and that is going. Oh, no, it's not. Okay. It's making some noise. Oh, gosh. That fell. I'm going to put that there. All right. So there's a couple sub-projects that all worked together on this drone to make it what it is. Those sub-projects are different people. They all were specialized in their own regard, so that way they can personalize what they designed for this drone. That way we don't have multiple people trying to design the same thing, because that doesn't get us anywhere. So one of those sub-projects was frame design, and if you took a walk around during the open house, you would have seen some of the stuff they were actually working on. But I'll do a little overview here. So one of the main thing they did was the design of the structure. And that was all, how big should it be? How big should our, horizontal members be? And then they also did weight distribution. They had to figure out where are we going to put our different components? Where should we put the heavy components? So our center of mass, they did center of mass calculations. So center of mass doesn't cause us to become unbalanced. And then they also designed the component mounts. So how are we going to mount the GPS? How are we going to mount our sonars? They had to design those, so they were either 3D printed, machined, they had to design all of that. Then we had propulsion. And propulsion, they mainly selected the motors and the propellers that we needed to actually lift off the ground. And in order to do that, they did thrust calculations. So they had to figure out what is our throttle percentage for when we're just hovering in the air. They had to figure out how heavy is our drone, how much torque do we need from the motors, all that stuff. They did calculations for that so they could do proper motor and propeller selection. And then they also did arm design. They basically figured out how long do our arms need to be, where should we put them on the drone. That way they meet our standards, what we need, they meet what we need to get off the ground. Then there was payload mechanism, and payload mechanism designed the part of the drone that actually competed in the competition and allowed us to compete in the competition, which was dropping the water bottles. Because in the end, that is our main goal of the competition, is to do that autonomously. So they designed the payload delivery method, and they also designed how we're actually going to transport the payload to each drop location. Then there was also electrical, and electrical was a huge part of our team, and we're very happy to have them this year. But custom PCBs, there's a printed circuit board. This is the first year we ever did custom printed circuit boards. And we decided to do that so that they met our specifications. Because in the past, we've had problems where, this circuit board doesn't quite, it doesn't quite work with all of our other stuff. Well, if we just make it custom to our situation, then it should work. Then we also did a lot of soldering. The L always messes me up. Soldering and wiring. And they figured out what gauge wire do we need to use? How big of a wire do we need to use for this? And then what type of solder? how should we solder it? Where should we solder it? They figured that out. And in doing that, they also did power budgets and block diagrams so that we could figure out how long are we going to be in the air, because that's very important. How often do we need to do battery changes while we're at competition? So I'm going to talk a little bit how a drone actually works. So in simple terms, the propellers spin, right? And then the drone goes up. But there's a lot more happening behind the scenes that you might not realize. And one of those things is contra-rotating propellers. Basically what that means is the propellers rotate in opposite directions. If you have 4 propellers on your drone, 2 of them are going to be clockwise, the other 2 are going to be counterclockwise. And that allows them to cancel out each other's torque so the drone just doesn't keep spinning in circles. Then you have what's called the PID loop, and that stands for proportional integral derivative loop. And that is a type of feedback loop, and if you were at one of the booths, you also would have heard a little bit about that. But basically, it keeps the drone stable by getting constant feedback from the different sensors on the drone, so the accelerometer and the gyroscope, so that it can stay stable in the air. It can figure out, okay, am I tilted like 5 degrees to the left? If so, do I need to correct for that, or is that what I want to do because I'm going in that direction? And what's cool about the PID loop is this technology wasn't around always. In fact, the idea of a multi-rotor aircraft has been around for a very long time, but we never had the technology to actually execute that design until we got the PID loop. So I think that's very cool. Another big part, and it might not seem like a big part, but it is a big part of having a drone fly, is airframes. And airframes, the airframe layout is very important because you have to specify what airframe you want to use for each specific purpose of the drone. We're going to talk about that for our drone here. So our airframe layout is what we call an X8 coaxial layout. And basically that means that there's 8 propellers. The 8 stands for propellers. X is, the shape that it's in. So if you look at the diagram, you have an X and you have 8 propellers on each arm, as opposed to a typical octocopter, which would have 8 arms and 8 propellers. Now, what's great about the X8 is, first off, it's coaxial. So it has 2 propellers to each arm, and they both rotate in opposite directions so that they counter out each other's torques on the individual arm, and then each arm counteracts the other arm's torque through counter rotation, as I talked about earlier. So like 4 and 3 are counter rotating, and 4 and 7 are counter rotating. Now, what's great about the X8 coaxial layout is it's way lighter because you don't have those 4 extra arms that you would on a octocopter with 8 arms, but you still have the same amount of propellers. That does come with a slight caveat, which is that you only have about 85% as much thrust as an octocopter. So you lose about 15% there, but the weight that you lose there, it definitely balances out. It's a much better, for our purpose, it's much better than losing a little bit of thrust. So, additionally, we also have a 3-level drone, and this is as opposed to like a 1-level drone where everything's just on, if you think about it like a house. You have like a ranch house, and that's just all 1 level, or you have a more vertical house that has multiple levels. So we went with 3 levels, and that allows us to not take up, our drone won't be so large, it'll just be taller. So we have heavy things on the bottom for more stability, and in the center, we have flight components, like the flight controller, the electronic speed controllers, and then on the top, we have our more expensive equipment. That way it's safe from all the moving stuff at the bottom and the ground when we're landing. So, we're going to talk a little bit about propulsion and the decisions that they actually ended up making. One of those things were what motors we were going to use. So we decided on motors that were designed for agricultural purposes, and that would be like the motors that are used on crop spraying drones. And those have gotten to become a much bigger thing in the very recently in the last couple of years. But one thing about these motors is they're brushless. They're a lot lighter than normal brushed motors. They also last a lot longer. They can last way more rotations than a brushed motor. They have so our specific motors that we've chosen, they prioritize efficiency over speed, as opposed to like a racing drone where you don't care about battery life as much and you want it to just be fast. We care a lot about battery life here, but we don't need it to be super fast. We don't need to go 60 miles an hour like a racing drone might have to. Now, it also has super high power because of this, and this is because the agricultural motors, they're designed for drones that are carrying these heavy fertilizers so they can spray them all over crops. So we desire that high power because we're also carrying very heavy equipment, such as our cameras and our Jetson, that's our big heavy computer, and the payload. We also decided on propellers, and we decided to use carbon fiber propellers over typical plastic propellers. And the reason why is because carbon fiber is super low weight, and because of that, it also has a really low moment of inertia. And that means that we can turn the propeller with way less power. We can keep it spinning with way less power. So that way all the power we put into the motor goes straight into thrust, and we don't have to spend any on getting the, we don't have to spend any power on getting the propellers to keep rotating. I got that out. They're also scratch resistant. That's good because any scratches that are along the propeller that get created along the propellers, they can create turbulent flow. And turbulent flow is going to make it harder for the propeller that's following it, because they're rotating, to push the air. And then it's a decrease in efficiency on thrust. So then we're putting more power into actually keeping the propellers from turning, and we're not moving as much air below us. Additionally, to increase efficiency, we decided to go with upturn tip propellers as opposed to straight tip, because upturn tip reduces the vortex caused by propellers, and that also increases the efficiency, because vortexes causes turbulent flow. So we also had aerial structures, and this was decided by frame design. So we decided first off on having carbon fiber cross members. Move some stuff here. This is a piece of carbon fiber that it's a replica. Well, it's not a replica. It's just exactly what we're using on the drone, basically. Now, the great thing about carbon fiber is it's super lightweight. This is about 3 pounds. And it can take a lot of load for the weight that it has a lot of load bearing capacity. And it can take that load in a lot of different orientations. Like you can bend it this way, this way, this way, and it's not going to break easily. The one way that it can break easily is if you have some sort of load that's separating the layers. Now, for our purpose, we are not going to be screwing anything in between the layers, so that this works for us very well. Another aerial structure on this drone is the shock leg assembly. And basically, that's just a fancy term for how we decide to put the legs on the drone. And so we have these shock absorbers, similar to a car. And the idea of these shock absorbers is to absorb any impact when we land, because not every landing is going to be perfectly and nice and soft. If you've ever been on a commercial airliner, and when you're coming down for landing, and you finally land, and everybody claps, well, right before you clap, there's a big bump, and then everybody's like, oh, should we clap? Because I don't know, maybe something went wrong. Well, think about how much worse that bump could have been if there was no shock absorption on the landing gear. So just like that, on the 737, you have shock absorbers on your landing gear to protect all the passengers on board. We have shocks on our landing gear to protect our expensive computers and our payload that's on board. Another great thing about the shock leg assembly is it's a dual member design, so the load distributes evenly across both members, that being the shock and the leg. If this was just a rigidly mounted leg into the bottom of the drone, it would most likely break, especially if during takeoff or landing, we kind of shifted horizontally, because that would put a load on it that we were not expecting, or we would not have accounted for. So, how did we actually decide on delivering our water bottles to the ODLCs? Well, we decided on parachutes. And one reason is because it's a very historical approach to this kind of airdrop method. It's used a lot in military applications, and it's still being used today. If you've seen any of the recent Mark Rober videos, you might have seen some of the zipline videos, and they are currently airdropping medical supplies in Africa using drones and parachutes. So here is our take on parachutes. Basically, we have this centerpiece, and it's kind of hard to see because of the lighting today, but there are some holes in the bottom, in the center picture. There's some holes in that shroud almost, and that's our canister holder. So this is our actual payload delivery system, and this is what we call the canister. Now, this whole thing basically folds up. You have the water bottle in here, and then this goes on top, and it slips inside of the bottom canister holder, and then there's a trap door that goes underneath it. Now we just fly, we take the payload to where it needs to go, and we're ready to drop it. The trap door opens, this falls, and the parachute's open, and it comes to a safe landing. So our canister you put the water bottle inside, and it's made out of this soft plastic. It's made out of soft polyurethane, TPU. It's a thermoplastic polyurethane. And you can bend this in any way you want. It's not going to break. And that way it takes a lot of the impact load, because even though this is going to be falling pretty slow, it's still not slow enough to not cause any damage to the water bottle if the water bottle just, contacted the ground raw. So this acts as a shield to absorb some of that damage, because any like contact damage or any noticeable damage is up to the judge's discretion on if they want to take off points during the competition. So we want to make sure that it's very protected. So we also made the canister completely conceal the water bottle so that there's no just like little dents that can be made on the water bottle, because they're kind of cheap water bottles, just like the ones you buy from Target. So, very important. Then, the parachute is made out of ripstop nylon, and basically that means it stops rips. It's very like thin woven mesh, and that makes it so that air just can't slip through, as opposed to like a wool blanket. The air is just going to slip through. And then we also have this hole in the center. You might be asking, well, if you don't want air to slip through, why do you have this hole in the center of the parachute? Here's a good, you can kind of see it better there. Well, the reason we do that is so that airflow can actually go through the parachute. If you didn't have this hole here, what would happen is air would try to go around the parachute. If you think about fluid dynamics, it's going to try and go around the parachute, and then it's just going to cause the parachute to collapse, and it's not actually going to work. If you have the hole in the center, the air can go through the hole, airflow works, and, well, now the parachute actually opens up and stops, it lowers our terminal velocity there. We also made it bright orange, and the main reason why is because if for some reason it drifts in the wind and lands in like a forest, we can find it easily. And those are the solutions that we decided for the hardware aspects of this drone.
Thank you, Luke. Hardware is really the core of this whole operation, and you guys did an amazing job this year engineering these designs. Next up, we will be hearing from Henry, our hardware electrical sublead, and he'll be teaching you about the electrical systems of the drone.
Thank you, everyone. I really appreciate it. And so I'm going to be talking to you all about the electrical systems that helps this drone actually fly. All right, so this is our first year doing a printed circuit board. And so we had a lot of challenges. And working with the team through trial and error, especially because we didn't really have many resources from past people, because it's our first year. And so the team stuck together, bonded, we learned through trial and error, and we eventually came upon our design for the printed circuit board. We used a CAD program called KeyCAD. It's a high-powered CAD program where we can create a schematic, which is like a wiring diagram. We can make our own footnotes, which are basically layouts for if you want a pad or if you want a through hole or any kind of things where you want to solder a component to. And so we create that. We put it all together in a PCB layout, and then we can submit it to a manufacturer to be made. And so this is our custom circuit board. We did this to fulfill our needs. And some of the needs we had for the competition was we needed a voltage regulator. Because as I'll touch on later, the batteries provide 24 volts, which is far too many for our sensitive equipment, especially our $3,000 Jetson NVIDIA computer, which we want to protect. And so we have a 12-volt regulator that we have on here. And so basically, it takes in that 24 volts, outputs 12, and so we can power that computer. We also have 5-volt regulators. And so that way, if we ever want to put a Pi on there, we can. And then we have some extra sensors for our sonars and other accessories that software might need. And so we actually do this by using a common port that you all know, USB-A, which is found on sides of computers. You plug it into the wall, stuff like that. And we're going to use that to transfer power. And the board distributes power in different ways. One using the voltage regulators. We also have power that goes straight through 2 corners of the board where we have electronic speed controllers, and we can control that. And the purpose behind this is the emergency stop button. So say we have an issue with our drone, which won't happen. Say we have an issue with our drone. We want to shut off the motors, but we want to keep the computers on. So if we didn't have this, everything would shut off. But we do this so that the computers stay on, but we can shut off the motors safely. All right, let's talk about soldering, another huge aspect of our team. And so we've soldered a variety of wires. We've learned how to solder, practice soldering safety. We did workshops, taught other people. And one of the things we did is we went from very, very small wires, 28 gauge wires, all the way up to bigger 10 gauge wires. And so to put it in perspective, you think of a car battery, those are the type of wires. And kind of touched on that, taught some members, just building the team up. We taught everybody about proper solder joints and wanted to make sure we had good connections with our systems, make sure weren't any cold joints or anything that could cause issues. And so the team did a very good job this year, tested everything. It worked flawlessly. And so I am very proud of the team that we have here on the electrical aspect. All right, and now let's get to power. So basically, we have 2 huge 23,000 milliamp hour batteries. And if you think about it, most devices, they don't use that much current. You're talking maybe hundreds of milliamps, but each amp is 1,000 milliamps, and we're running quite a bit. We're running about 46 amp hours. And so we have quite powerful batteries to provide enough power for our drone, because we have a really big drone that uses huge agricultural motors, 20-inch props and everything. And so this will give us plenty of flight time for the drone. Current estimates put us around 10 minutes, but we are going to get up to 15 to 20. And so the batteries are actually linked together in a parallel circuit. And all this means is the amps come together, the current increases, but we keep the voltage the same. The voltage is constant throughout with 24 volts and a 6-cell battery. And another big thing we wanted to do was have intermediate connections because let's say something did go bad. Let's say one of the motors was having an issue or we needed to swap a part out. We have intermediate connectors, so we just unplug it, swap it out, and plug it back in. There's no need to remove the whole plates and everything, resolder everything. And so that's a very big, important aspect of our drone. All right, and now we get on to motors and ESCs. ESC is an acronym for Electronic Speed Controller, and we have T-motor ESCs, and they can go up to 70 amps a piece, and we have 8 of those. And so currently we have speed controllers that are operated by our flight system. They tell the motor how much current to draw, like how much power. That way we control the thrust. We use the computer to tell the drone what to do, how to stay up in the air, like how much power to use. And the drone is very powerful. We're able to get up in the air with just 30%. And we use 3-phase power just to control the motors, how they spin. And just like the intermediate connections, these are also swappable. We went with special connectors so that they can fit in through the arm. And so, because if we didn't have this, well, the whole arm has to go out, and we have to desolder it. And so these special connectors fit through our arms, which are meant to be smaller, so that we can be more aerodynamic.
Thank you so much, Henry. Each year, our team is making big steps forward in our drone technology and design, and I think that electrical in particular, we have taken some huge leaps forward this year. Next up, we will be hearing from Connor, our chief software engineer, and he will be giving you a software overview of the drone.
Hello, everyone. So, software this year is made up of 4 core divisions that all contribute to the SUAS competition. First of which is our flight team, which is primarily composed of autonomous drone control, as well as integration with other hardware devices. There's also the vision team, which works with controlling our camera. They also do some vision algorithms and calculations in order to detect standard objects or other types of objects that we need to detect during the ODLC and airdrop portion of the competition. There's also the simulation team, which works on testing all of the functionality prior to that. So testing our flight algorithms, testing our vision code, making sure everything works properly. We've also added a research and development aspect of our team this year, dedicated to testing, or really logging most of our tests that we perform throughout the year, as well as working on a lot of miscellaneous projects. So the first thing I'm going to discuss today is our autonomous drone control. So for the SUAS competition, we need to fly that 3-mile waypoint circuit that you heard about earlier, and we try to accomplish this in a variety of different ways. First of which is through our path planning algorithms. So we utilize an A-star pathing algorithm. Now what this is, it's just a shortest path algorithm that we can set up the parameters for within code specifically. So this is entirely competition and environment dependent. So what that means is that we have to create a new waypoint path for whatever environment that we're trying to test within. So for Multirotor, we have a testing field at the old golf course right across the street from the hospital in Rolla. So we have to set up pathing algorithms for this golf course, as well as for the actual competition environment, which is going to be in Maryland. So we have to ensure that this pathing algorithm works for the actual competition environment, as well as what we're trying to test in Rolla right now. So this is dealing primarily with high-level movement planning. So this is just, we have to create the full waypoint path before we complete the other aspects of the competition. So what we need to do is map out a full waypoint path through the entire boundary that we're allowed to fly in first before we try to accomplish any other tasks for the competition. Now this contrasts with our offboard control. So we utilize offboard control for more shorter bursts of movement. This type of movement deals in more primitive movement schemes. So what that means is we deal with the actual pitch, roll, and yaw of the drone itself. We directly control that through software commands. And this is more so for obstacle avoidance. So we need to ensure that we obviously don't crash into anything during the competition. And we utilize offboard commands to make quick bursts of movement to avoid anything that might be in our path. And like I said before, we can integrate this offboard commands with our hardware devices, some of which I'm going to talk about a little later. So for the computer vision parts of the team, we have to deal with detecting 2 different types of objects for the airdrop portion of the competition. So we need to drop these payloads, the water bottles that were mentioned before, on 2 different types of objects. First of which is the standard objects, an example of which you see on the left there. These are composed of an exterior shape, a character or number within that shape, and also a color that's filling the entire shape itself. So to detect these shapes, we have to run a few different algorithms, first of which is contour detection. We have to utilize contour detection algorithms to figure out the exterior shape for this standard object. And then from there, we can actually classify that based on the contours we found from our photographs that we take during our flyover. And then next, we have to utilize color correction and detection algorithms to figure out what color is actually contained within those shapes, and we can pass that on to our flight process. The other types of object are the emergent objects. This is literally just going to be a mannequin that's going to be out on the airdrop field that we have to detect with our vision algorithms. So again, we're going to utilize the shape detection algorithms to map out an actual person shape as they lie on the ground out in that field in Maryland. We also need to utilize clustering algorithms to detect these person-like shapes. So for the competition, there's going to be a few different judges actually out on the field grading like the water bottle quality, how close it was to the standard ODLC location. And we have to utilize these algorithms to ensure that we can detect which one's the emergent object and which one is an actual judge, so we don't drop the water bottle on a judge by mistake. So in order to accomplish these tasks, we have to utilize a few different learning schemes to ensure that our computations run quickly. Now what we use as the vision team, we utilize a YOLO V8 neural network algorithm. So this is just a learning strategy that we utilize to make our computations much quicker during the competition space. So in order to accomplish this, we need a very large data set of those standard objects to ensure that we can cover all of our bases during the competition space. There's going to be a lot of different combinations of colors, shapes, what characters are going to be within there. We have to account for all of those possibilities. So we utilize these large data sets to train these models. Now what that means is just we have to run all those algorithms a bunch with all these different combinations to ensure that we can calculate efficiently during the competition time. So we can train our model utilizing a large data set that we're going to generate in a second. So for the payload system, it's controlled through these 3 servo systems you can see here. Now we interface with the servos via serial code during our flight operations. So, like I mentioned before, we have to drop these water bottles onto specific ODLCs, right? And we can communicate between flight and vision utilizing a file sharing scheme. So when we run those vision algorithms that I mentioned before, we have to pass data to flight to ensure that we can move to the right ODLC and drop the proper payload utilizing our 3 servo system here. Now the reason why there's only 3 versus 5, since we have to drop 5 in total for the competition, is we wanted to reduce the weight on the drone and also allow us to change out batteries if we need to during the actual flight competition. So those batteries that were mentioned before, we might have to swap those out if they get a little low, and we also need to refuel our payload mechanism with the remaining 2 water bottles for the competition. So the communication between flight and vision is a very important aspect of the airdrop in particular, since we need to communicate these ODLC data between the 2 and ensure that we're dropping the correct payloads on the correct ODLCs. We can get as many points as we possibly can. The next aspect of software I'm going to discuss is our simulation team. Simulation has been a relatively small team on software in past years, but thankfully this year it's grown much larger and they've been able to expand their operations. So they've recently been working with Unreal Engine and Microsoft AirSim to test out drone physics in a nice 3D environment. Now, a large project that they've been working on recently is actually creating a full 3D competition environment. So this is we're trying to make a full environment in Unreal that's basically almost one-to-one to the Maryland competition space that we're going to be competing in. So they need to import their own textures for those ODLCs. They need to import new models like for trees or other types of obstacles in the way. We're trying to make a very accurate representation of this competition space to provide a very accurate training space for our flight and vision code. So simulation integrates with flight and vision in a variety of different ways. First of which, the obvious, is that we can run all of our flight algorithms within this Unreal Engine to ensure that we don't crash the drone by mistake in the actual competition space. So we can detect these pathing errors that might occur with the A-star algorithm, and also test out the offboard commands to ensure that we're not moving in a very strange orientation. We're not crashing the drone by accident by attempting to do these high bursts of movement with the offboard commands. Simulation has also been very active with the vision half of the software division. They actually are generating that large data set that we need to test our vision algorithms entirely in Unreal. So what they do is they randomly generate different standard ODLC combinations to ensure that we can meet all those test cases for like strange combinations of ODLCs. If there's any warping on the shapes in a real scenario, we need to make sure we can run those algorithms efficiently on any type of scenario for the competition. So the last aspect of software I'm going to discuss is our research and development side of the team. So they've been very involved with our collision avoidance research. So in previous years, we were trying to use LiDAR, which I mentioned in the open house section, for obstacle avoidance. However, there are a variety of reasons why we decided to not roll with that this year. First of which was the LiDAR system is very heavy, and we wanted to reduce the weights on the drone this year as much as we can. Also, the LiDAR is very difficult to integrate with our code based on our firmware that we use. So we decided to go with ultrasonic sonar sensors this year because they're also much smaller devices. They will fit on the ends of each arm of the drone, and we can utilize those to detect objects that might be coming near our drone, so we need to avoid those utilizing the offboard commands that I mentioned earlier. They're also much easier to integrate with code. We can control them with our firmware as well as within our testing platform, Q-Ground Control. They're much easier to work with than the bulky LiDAR. The other project that the R&D team has been working on this year is our flight logger application, which we call Compact. This is a Svelte kit application that we use primarily for logging purposes. So when we're out on the field, we can efficiently log all the information we need for our own purposes as well as for campus health and safety department. So we log the flight time, how long the drone was in the air, what weather conditions we were flying in, what type of tests we were running, and other types of information we might need for our own purposes or for anybody else that might need to understand what we've been working on in past weeks. So R&D has been very useful for us this year for aiding our logging process as well as assisting us with our obstacle avoidance algorithms.
Thank you, Connor. This programming is intricate, complex stuff, and we have some insanely talented members on our team that they're able to piece together this software. Now, lastly today, we will be hearing from Alen, our software flight sublead, and he'll be telling you about the state machine.
Thank you, Rose. As Connor mentioned, we have a lot of software members working on different parts of the code for different phases of the competition, and we needed a solution in order to combine all these parts into one full competition code base. And so we had two real requirements for this solution. One was that it would be able to go through a full run through. We would just be able to press one button and be ready for competition, not have to do anything else, just not worry about it. And two, it had to be modular, so we could run different phases of the competition at different times just to test the functionality of it, make sure it's all good before we do one full run through. And so our solution to that was the state machine. So before we talk about the state machine, we first have to talk about what states are. So at the beginning of the year, when the SUAS rules were released, we went through the rules. It's around like 20 pages. We simplified it, and we basically found 6 different phases of the competition. These phases require different parts of the drone to be active or controlled. And so for each state, we needed a separate implementation. And as I mentioned earlier, we needed these to be modular so we could test one at a time. We didn't have to do it all at once. And so there's 6 states. First is start, which just connects to the drone. Second is takeoff, which just launches the drone up into the air. Third is waypoint, which does our 3-mile waypoint flight. Fourth is object detection, which uses our camera and scours the ground for objects, taking pictures along the way, and using our vision code in order to tell what these objects actually are. Fifth is airdrop, which drops the bottles at the locations that we recorded the objects that we found during the last state. And then land, which just lands our drone where we launched it from. And so if you lay these all out in a path, you get a pretty linear path, right? It looks pretty simple, looks pretty easy to implement, right? Just go from the first state, second state, third state. Looks pretty simple, right? Well, unfortunately, due to SUAS rules, it's a lot more complicated than that. For example, whenever we want to drop another bottle after the first one, we have to go back and do our entire waypoint flight all over again. So we have to go back and forth. It's not just one simple path. And then also, after we've been through the object detection state once, we don't have to go through it again. We already know where all our objects are, so we don't have to go find the objects again. We have these locations recorded. And there's a couple other considerations we need to think of too. First off, what if we need to manually take over the drone? One part of the SUAS rules says that if we have to manually take over the drone, our safety pilot, if he has to take over, fly back to where we launched it so we can do some changes or any safety changes, we have to stop all code from running. So that's a consideration we need to think of when we're implementing the state machine. Second, for saving the competition progress, if we ever have to change the batteries, we obviously lose power to the computer. And so we need to save the progress of our competition in a place where we can restart it from. We can read it after we've replaced the batteries and then start just where we left off from. And then lastly, circular dependencies. This is kind of like a software-specific issue. Basically, if you have one state that depends on another state so you can run it, and then that state then depends on that state, you're kind of in an infinite loop there. It's not really something you can implement. It just gets stuck in a loop. It won't run. So you have to find a way around that so you can actually run the code. And so our solution to all those problems is the state machine. So instead of each state leading to the next state, we have the state machine, which basically asks for an initial state, waits for the result of that, and then uses the result to see which state it should run next. This allows us to be very flexible. We can start at any state we want if we want to test anything. Allows it to go in any path at once from any state to any other state. It also keeps track of our progress across the competition. Between every state run, we basically have a function that just records all of our drone data in a file, so that if we have to restart the state machine, we can just read that file and we're all good to go. One of the very important parts of the state machine is the kill switch. If you think about a physical kill switch, especially on a drone controller, what it does is it basically cuts off all functionality of the drone. If you have it on, you can't start flying, you can't turn on the motors. It's supposed to be safe so that you can go pick up the drone, move it somewhere else, and you'll be all good. So we need something like that for software as well. If we have our safety pilot trying to save the drone, if our drone's doing something unexpected, we need him to be able to have a comfortable flight back to where we launched it from. If code's running, it's going to be pretty rough to try and fight the drone and get it to go where you want. You can kind of think of it as a car with power steering. You know, with these newer cars, you know, you try to steer, it's pretty smooth. You can make the car, you know, go whichever direction you want. And then you go to an older car and you're really fighting the thing to try and steer, especially if you're doing a tight turn. So we don't want our pilot to have to deal with that. So the state machine watches for manual takeover status, and if it detects that our pilot's trying to take over, it'll kill all the code and just let our pilot drive without any interference. And then once our pilot's done landing, it'll be able to be restarted, the state machine, from wherever we left off from. So we don't have to start all over again. We're just good to go, restart it right where we left off, no interruption. And then lastly, there's graceful exit. If the code were to crash or have an unexpected failure or anything, we don't want our drone to just be waiting in the air, even though we have a safety pilot. So if our state machine detects that the code has crashed or anything, it'll basically safely, autonomously return it back to where we launched the drone from. And so our safety pilot won't have to deal with the flying it back if he doesn't have to. If we can do it autonomously, if we still have good connection, why not just do it autonomously?
Thank you so much, Alen. Now, the team has put together a video that we'd like to share with you all.
The SUAS competition has the drone go over 5 different target landing zones and drop the water bottles on the specific designated target. We have a 3 canister, meaning we're going to have to do 2 rotations, but the drone parks over it and it just pops open the canister and then just falls down.
So this year I've been heavily involved with making the leg mounts for the drone, and we kind of wanted to make something similar to like car suspension. So we wanted to have like a shock that absorbed the impact whenever the drone landed. We kind of just started by looking at how, I guess, car suspension works and looking at how there was springs in that, and we wanted to incorporate a shock or a spring on our design.
We're working on making a vision data set in Unreal Engine for Vision to test their code and train a computer vision model with. The vision data set is to just make sure it works before competition.
Our big project this semester has been the state machine. What the state machine basically does is splits up the competition into 6 different phases and then runs the corresponding code for each of those stages. And since there's a lot of different transitions we might need to do, like we might need to go from waypoint to the airdrop, but after airdrop go back to waypoint, we've just been hard at work implementing all that into the code. Getting to see the drone actually run our code that we've been working on for a year is a really fulfilling thing to see, I guess.
Long-standing tradition of only naming our drones after they've taken their first flight. And ladies and gentlemen, that time has come. If you would please turn your attention to the left for the reveal of our 2024 SUAS drone. And flight time. And now to reveal the name. Yes, can I get a drum roll, please? The name of the 2024 SUAS drone is Goose. And that's about all for today. I'd like to thank you all one more time for showing up. I'd like to thank all our speakers. You did a fantastic job, and yeah, thanks for coming down, guys. house will be open for another hour and a half if you'd like to stay and look around.
Thank you all for tuning into our live stream. We really appreciate having you with us for this event, and we hope you have a fantastic rest of your day. And we would love to have your support in helping Multirotor fly the future. The donation QR code will remain up for a few more minutes. Thank you.